recording and then. Okay, so we can start now. So today, good afternoon, everyone. Today we have Ananda Maity, a postdoc from Okinawa Institute of Science and Technology. So he's currently still affiliated there, but probably he will very soon move to SN Bose. And today we'll talk about some aspect of entanglement theory. So Ananda, you can start now.
Thank you, Mita. So yeah, as the title suggests, so I am going to talk about maximally entangled mixed states for a fixed spectrum do not always exist. So why this result is just published few months ago in Physical Review Letter, and why this result is important. So in order to motivate, so I would present this slide where you can see there is a maybe some of you know that there are some set of open problems published in this IQOQI Vienna's website. So there, this fifth problem was the maximally entangled mixed states, and it was open from 2001. And when I am talking about maximally entangled mixed state, I need to define what is the notion of maximally entangled mixed state, because so, if I say maximally entangled, you can think of, okay, in a two-qubit system, it's a Bell state, right? Phi plus or phi minus or psi plus or psi minus. But when I'm saying maximally entangled mixed state, then what does it mean? So what they are saying, so among all density operators of two-qubit with the same spectrum, one may look for those maximizing some measure of entanglement. So it turns out in this paper by Verstraete, they show that for some of the measure of entanglement, like entanglement of formation, relative entropy of entanglement, and negativity, one gets the same maximally entangled state. I mean, the same states which actually maximizes all these entangled measures. Then is this the maximally entangled state? Because you can actually be, I mean, when I am saying that some of the entanglement measures are maximized for that particular state, that means you can think of, okay, that state actually contains the contains actually maximally entangled states, contains the maximal amount of entanglement. But is this because? But there may be some other entanglement monotone which may not be maximized for the particular state. So it is just a they just find it accidentally that only these three measures are maximizing. These three measures are maximized by that particular state, or all entanglement measure will be also maximized. So they keep it open because in general it's very hard to characterize entanglement for mixed state even for two-qubit system. So yeah, so that is the motivation, but I will explain more. Then you will it will be more clarified what do I mean by maximally entangled mixed states. So but just to mention that this was an open problem for 20. Okay, so before going I have to first before going to the details, I have to first introduce the resource theory. So whenever I am talking about some resource theory, it actually has two components. So I need to say about the set of free states. And as I mentioned, the set of free states, again, the notion comes free operation. I mean, you cannot define free operation or free state alone, because the free operation is the property that it is closed under composition and it maps free states to free states. So for example, if you consider the entanglement theory, free states are the separable states and free operation are the local operation and classical communication. Means you do on your local lab whatever you want, and you do classical communication among these two distant laboratory. That is your free operation, and you cannot increase entanglement by that free operation. So, and yeah, also if your state is separable, then you cannot generate entanglement. So this is the basic structure of entanglement theory. I am not just saying it briefly. It may also require one full lecture, but I'm just mentioning briefly that this is the structure of the resource theory. So there are some free state and free operation. So for entanglement, it is LOCC is the free operation, and the set of free states are separable states. So then the question arises, let's say you have some state rho, which is a density matrix in so let's say you have a set of all density matrix D, and rho is one particular state in that set of density matrix. And let's say your free operation is LOCC, and you want to go from rho to sigma by LOCC, under LOCC. Means local, by performing some local operation and doing classical combination, can you grow from rho to sigma, where sigma is again another density matrix? That is the question. So now to motivate, let's consider some examples. So let's say Alice and Bob are sharing this state, this maximally entangled state, just 0 0 plus 1 1. So can you go from 0 0 1 1 to 0 1 plus 1 0 by LOCC? Yeah, you can go, because you just apply this local operation sigma x on Bob's side, then you will get this state. So similarly, if I ask that from this 0 0 plus 1 1 2, can you go to this pi minus state like 0 1 minus 1 0? Yes, again it's a local unitary. Again, you can apply just a local unitary sigma x sigma z on Bob's side, and you can go. And now also I can ask, let's say you have this maximally entangled state 0 0 plus 1 1. I mean, I'm saying maximally entangled, although I have not defined the notion of maximally entangled, but you all know, that's why I'm just saying. So 0 0 plus 1 1 2, let's say your state is just 0 0. So can you go by LOCC? Yeah, you can do it. You can actually prepare the state 0 0 by just classical communication, and Alice and Bob can just prepare. They just do the classical communication and they just prepare this 0 0 state. And even I don't need to use the state. I can prepare the state. So you can also go by LOCC. I can prepare the state 0 0. Can you prepare 0 1? Also yes. Now if I ask the question, can you go from 0 0 to 0 0 plus 1 1 state? I mean, it's a separable state and it's a entangled state. Can you go from 0 0 to this entangled state? Definitely the answer is no, but then why not? It's increasing the entanglement by LOCC, but I said the LOCC is a free operation, and by under free operation you cannot go from, this is a separable state, you cannot go from separable to entangled. I mean, under free operation you cannot increase entanglement. Anyway, it needs more characterization how the state transformation are actually happening. So you cannot go. Now if I ask you, let's say there is some tripartite state. So if I ask you like some states like 0 0 0 plus 1 1 1 state, like which is called GHG state, is distributed between these three parties. Now if I ask you, can you go to some other state which is 0 0 1 plus 0 1 0 plus 1 0 0, which is a W state? Can you go? And again, one can actually show that by LOCC you cannot go from one to another because they belong to different classes. But anyway, for this, I mean, so what does we mean? What does we learn from that? That actually, in order to go from one state to another, we need some characterization. And so far I give just example for the pure states. And yeah, so you cannot go, but yeah. So then we need some concrete structure of the state space, concrete structure of the pre-operations, under which pre-operations. So for everything I am talking about in the under LOCC. So it needs some much more characterization of the state transformation laws and what are the states. So okay, so before proceeding, let me just define what is LOCC. And LOCC, you know, it's a classical, it's a local operation. Let's say there are two spatially separated parties and they are performing some local operation on their respective lab and they are communicating classically. And this is just my LOCC operation. And I should not write it's no concrete mathematical structure. Rather, I should write that the structure is a little bit complicated. Means is the mathematical structure is not that much useful or handy. And so in order to characterize some state transformation laws under LOCC, people do it in some higher class of operation, which is called save operation. And what is save operation? Save operation is a, let's say you have a CPTP map lambda, which is from, let's say, d-dimensional density matrix, set of d-dimensional density matrix to another d-dimensional density matrix. It's called shape. If it has a Crouch decomposition like this, that lambda rho equals to sum over I xi rho xi dagger, where xi are the Crouch and it is sum up to identity xi dagger xi, and this xi has this form ai tensor bi for all I. So that means this xi can be written in some separable form. So then this operation is called shape, and this is actually okay. And I define another operation which is called non-entangling operation. So what do I mean by non-entangling operation? It is a CPTP map lambda.
Sorry, can I ask you something?
Yes, sure.
I mean, yeah. So I mean, this AI and BI. So BI is in which party? Like you're going from D to D prime, right? So for example, Maybe
Yeah.
A to B.
So this is an overall. I mean, this is a set of density matrix. Let's say in the two cross two. I mean, it's 4 cross 4 matrix. That means it has two C2 tensor C2. If you say, then AI and BI. AI belongs to the first Hilbert space C2, and BI belongs to the another Hilbert space C2. Like that.
Okay. And D
I
and
mean,
D prime.
Yeah, I should say not belong to C2, rather than the operator of that C2. Yeah. So sorry, you are asking.
So I mean, this D and D prime. I mean, there is no restriction, right? I mean, D prime could be greater than D, or it could be also less than, right? I mean, there is no restriction on the dimension of D prime.
Yeah. Yes, there is no restriction because it can also be some isometry. Yes. Yes, it can be also some isometry.
Yeah. So isometry is a special class of ECP operation.
No, that depends on, like, I mean, isometry can also be just a global unitary, right? But that depends that this has some structure. AI tensor BI means this first Hilbert space, the operator belongs to the set of matrix of the first Hilbert space and the set of matrix on the second Hilbert space. So that is the structure. So
Yeah,
isometric can be a global isometry also, but I'm saying the structure should be like this. Yeah.
Yes. Okay. Thank you.
Okay. So then,
Ananda.
yes. Sorry.
Yeah, this XI, this product form, that is important. No, not even separable correlation is allowed. It's strictly
Yes.
product form.
Yes.
That is important. No, even separable means convex mixture of these things will not be allowed.
Yeah, so XI are actually yeah, they are in the product form. Yes, means.
Yeah, that's
But yeah. So yeah. So now if I say what is non-entangling operation, it is just another higher order operation, which where my demand is even less. So my demand is only that. So a map is called lambda is called non-entangling if it just map from SD to SD. Where what is SD? SD is the set of free state actually means. Sorry. The SD is my set of free states, means like so this is a set of all density matrix, and if this is my set of free states, then under lambda my demand is that okay, if this state, if any state you took from here, it will go always to this S. So then if the operation is such that just it preserve the set of free states, then I call it the non-entangling operation. This is even so it can be people show that it is actually LOCC is a strict subset of SAVE, and SAVE is a strict subset of this non-entangling operation. So then yeah, any question?
So I mean,
Ananda,
okay,
sorry, Tanmay, you proceed.
Yeah, I mean, my question is like, I mean, this kind of operation, like, this is, I mean, you were talking about entanglement resource theory here, right? I mean, if we come up with some other resource theory, like one can always define this kind of operation. I mean, here the idea is you don't increase the resource, right? This is the idea,
right?
Of defining this map, this lambda map, right? I mean,
Yes.
in principle, it should be extended to other resource theory. Am I right?
Right. I mean, actually, resource theory itself is when I am saying about resource theory what with respect to some pre-operation. Here, for entanglement, resource theory, the pre-operation is LOCC, but you can also define another resource theory where pre-operation is SAVE also. So, I mean, actually, people so I mean here even for all these operations, entanglement is actually you can define the resource theory of entanglement. Considering the pre-operation as LOCC, SAVE, and non-entangling operation, but you can also define some finer resource theory where say you define some SAVE operation is your pre-operation. I mean, you can define some, this may not be you may not call it this set of resource theories. I mean, some kind of different resource theory, but depending on the what kind of pre-operation you are choosing, you can modify your resource theory. So for entanglement, LOCC as well as SAVE as well as non-entangling operation, both all are pre-operations in some sense, and non-entangling operation is the largest class of operation that can be considered as pre-operation in the resource theory, because it preserves the set of free states. You're right, actually.
So Ananda, I'm saying just like a LOCC, there is no concrete mathematical structure. SAFE has a concrete good mathematical structures. What about non-entangling operations? Is there any concrete mathematical structure of this kind of operations?
Yeah, so here again, non-entangling operation. Yeah, what we are so in this paper they are using it's just the set of free states remains as free states under this map.
I see. I see.
But yeah, that operation is sufficient to characterize this. Let's say when I will proceed, will show that that operation is sufficient to characterize the set. But I'm saying, if you want to characterize such kind of set, what we are going to do in that some
how the cows will look like in the non-entangling
yes.
operations. I think it might be as complicated as LOCC. I don't know. I'm just guessing.
Okay, I don't. Yeah, maybe I don't know.
Because whenever I see the non-entangling operations, it is always like okay, it is not creating entanglement, that kind of statements. But I never see the
mathematical structure.
Good representations like a set operations.
Okay,
yes.
I see. Yeah, but what? Yeah, sorry.
Yeah, in case, like basically, this lambda mass is tells about the state transformation rule for the resource theory, right? This is the purpose of this operation. I mean, but I think if the resource theory is convex, this is always possible. There is a paper, like I can send it to in the group. If the resource theory is convex, we can always define this state transformation rule for any kind of resource theory. But resource theory has to be convex, otherwise.
Yeah, it has to be convex, right. Because otherwise, yeah, you can go outside of the state. Yes. Sure.
No, Tanmay, what you are asking, can you just mention once again what you are saying?
I'm asking about this any operation, like in this case is a non-entangling operation, but I'm saying like this is always possible to do this kind of operation lambda, which doesn't increase the resource. It is always possible if the resource theory is convex. Like there is a paper about it.
Obviously, yeah. Okay. But okay, no, but we are not. I'm not asking that one. By the way, just from your questions, let me just tell you. I think Manikda can confirm. There is some monotones, which is there is some quantifier. Okay, there is some functions which is monotone under shape operations, but not monotone under LOCC. Okay.
Yeah.
So there is some quantifier which is monotone under shape operations, but does not follow the monotonicity under LOCC. So according to the entanglement resource theory, entanglement is increasing, but shape operation would say no, it is not increasing. Right? Am I correct, right?
Yeah, I exactly forget the reference, but there is some result probably. Yeah.
There is some result, yes. So that's why this when we talk about the resource theory of entanglement, we have to stick into the free operation as a LOCC, because if we think that okay, my free operation is increased to shape operations, then some of the entanglement quantifier might increase.
Oh.
But Mirda, I was asking that since LOCC is a subset of shape operations, so if you are saying that this quantified is a monotone under shape operation, doesn't it automatically captures this LOCC as well? LOCC is a subset.
Need not to be, right?
No, I think Pratik is correct. Reverse may be true. That some quantity which is monotone under LOCC but not under shape.
That may be the case.
Monotone is, I think, it should be monotone under LOCC, but
not under
monotone under shape.
Not under shape. So that's why okay, I swapped these things, yes. That's why I'm saying that when we say the free operations for entanglement theory, I think it has to be LOCC. That could be one reason why we take only the LOCC as a free operation. I don't know. My guess.
Yeah, but here what will show that actually you will consider some entanglement measure, which is actually if it is an entanglement measure is the monotone under the non-entangling operation, then it's also a monotone under LOCC. What Pratik you are saying, and so we will comment. Yeah.
Yeah, Ananda, that is true. If as a monotone wise, as a yes, sir. Okay.
Yeah.
So if you can prove something is monotone under a bigger class of operation, probably that is you can prove monotone under a smaller class of
Smaller,
operation.
yes,
And
yes.
and someone is allowed to use that freedom. But what
Yes.
probably Mir is trying to say, physically, operationally, if you want to define entanglement, resource theory of entanglement, then
Okay.
operationally motivated definition should be
Is LOCC.
LOCC. Because
Best.
you can mathematically define a resource theory of entanglement as SAFE. So
Hmm.
SAFE is now free operation.
Hmm.
Now you should not demand that to implement this free operation I require entanglement. Because there are some SAFE operation you cannot implement by LOCC, you require some entanglement. So free operation by definition we should not, some resource consumption should not be there to implement this SAFE operation.
Yes,
Free operation. Like example, Bennett basis. It is a separate application. But you cannot implement by LOCC. But what they will prove, that is allowed. If you want to prove something monotone for under bigger class of operation, you can prove, okay, then you can extend that conclusion for a smaller set.
Yeah. So yeah,
That
what you are
probably they will take. What you are
yes. So maybe better, it would be better like if I don't say it as a resource theory of entanglement, but the structure is allowing to do all the things. But actually, I should not say it's the non-entangling operation is a free operation for resource theory of entanglement. That's what you are trying to point out.
Exactly. But something like if you want to prove something monotonic behavior, I go to a bigger class of set that is set. There I might be, it is easy to prove, and then I conclusion come to at LOCC level. That is a bona fide thing.
Yes. Yeah, agree. Yeah. Okay.
But Manikda, so you are telling that if we want to perform the Bennett basis measurement using LOCC, then we need some entanglement assistant. So it is resource consumption operations.
Yes.
Right. But it does not mean that SAFE operation is to perform SAFE operation, you need entanglement. You are restricted your operation as LOCC, then to perform the SAFE measurement, you need entanglement. But if you are in same lab, Alice and Bob are in same lab, then why we need entanglement to perform the same measurement?
No. You try to understand. You want to capture the resource theory of entanglement. Okay. So entanglement is zero resource. Now, whatever free operation you will define, should that free operation should consume a resource to implement that?
No.
So, but for SAFE operation, it is required.
Why? How?
So, Bennett basis measurement, is it LOCC implementable?
No, it is not LOCC implement, but why you are taking the LOCC framework here?
What framework I will take? SAFE framework.
SAFE framework. They have to
but your aim is to understand, capture the resource theory of entanglement.
Yeah, they have to be in same lab.
So by just without entanglement, you can implement Bennett measurement. Are you suggesting that? That's my question.
They are in, if they are in same lab, then they
what do you mean by that? It is resource theory of entanglement is separate.
No, you are assuming that the framework of entanglement resource theory, the parties should be in different lab or distant lab. But this is not justified, Manika. Though the non-triviality of entanglement generally revealed through these distant lab tasks, but to define the resource theory, I don't think this is needed that the parties should be in separated labs.
Yeah, that's depend how you are defining the resource
What you
theory.
mean by separate all these things, that's not very clear to me, because I'm saying separate all these things. My question is, Alice Bob is together at same place, everything you use, but I will not allow you to allow between them any entanglement. Can you implement Bennett basis measurement? That is my question.
No.
That's my question on it. It is
No,
whatever.
in this framework, no.
Okay, we can discuss probably.
Okay.
Let's go to that.
Okay.
Yeah, so I agree that you can say actually that this non-entangling operation, I mean, I should not say that this is the under the non-entangling operation, I should not say that this is also the free operation for the resource theory of entanglement, but what I'm trying to say is that this is a bigger class of operations. If you characterize something there, you actually characterize something under LOCC, and that is what we are going to use for some of the next slides. Okay. So before going to the details, just some basic things I need to introduce, because that will be useful. So for the time being, from now onwards, we will be stick to 2-qubit states only. And we denote, as we also introduced earlier, D and S as the set of all 2-qubit states, which is the D denotes for this set of the density matrix, and thus S will be the set of separable states. And the elements of D, as you know, is just a 4x4 unit trace Hermitian and positive similarity matrix. And the elements of S are just matrix rho, which belongs to the set of density matrix, but with some certain conditions that it can be written as pi psi i tensor chi i, where psi I and chi I again belong to this C2 for all I. And as I also defined earlier, this map lambda is called non-entangling if it belongs to this set of separable states. For all rho belongs to this set of separable states. So then there are some well-known lemma. So that if you consider the Bell diagonal states, which is just sum over I, pi, phi I, where phi I are the maximally entangled states. Here, this phi 1, phi 2, phi 3, phi 4 are just, as you know, there is phi plus, phi minus, I minus. And if all the pi's are greater than 0, then it will be entangled if and only if at least one of the pi is greater than half. Otherwise, it will be separable. And given any state rho belongs to this set of density matrix, we define the fully entangled fraction as you apply this local unitary UA tensor UB on phi 1. And take the trace of rho into these things, and you maximize over all possible this local unitary. Then you just take this maximization over all possible this UAUB. I will call it this fully entangled fraction. And also it can, if f rho is greater than half, then rho is entangled. So we have then this. Yeah.
This UA and UV, I mean, this is a unitary, like it's a two-dimensional unitary, right? So, I mean,
yes.
Does it have some restrictions that it has to be from the Haar measure, or it could be anything?
It could be anything, because you just rotate phi 1 to another, I mean, just by some local unitary, you rotate phi 1 to some another maximally entangled state just by some local unitary. But that should maximize your trace of rho and these things. So it could be anything, right? Because you can just.
I mean, yeah. I mean, my question is like, I mean, yes. I mean, I understand your definition, but my question is like, I mean, like you want to rotate, but I think it's possible to do even using this Haar measure. Like if you choose unitary from the Haar measure, like it will essentially cover all your.
No, it is not only Haar. So when you are saying Haar measure, so that means you are fixing your 2-qubit unitary only 4 unitary, right? Are unitary sigma,
no.
that, or are you saying something else?
No. Haar measure is not this. Haar measure is a U2 group. So
okay, like I'm saying what he is going to say that okay, if you just forget about this UA-UB, this you replace that things UA tensor UB phi 1 UA dagger tensor UB with some maximally entangled states, just a maximally entangled state.
Yes.
You just forget about this unitary, yeah. You just think a maximally entangled states, and that maximally entangled state is always achievable from some U tensor UB from phi 1. He's actually thinking about this thing.
I mean, in principle, is it possible to calculate for an arbitrary rho?
Arbitrary rho, yes. In principle, it is calculatable.
Oh, okay. I mean, can someone send me some paper like about these entanglement fractions, like where they calculate? Like,
sure.
Ajay, may I comment on this?
Yes, sure.
See, actually what is happening over there, that all the maximally entangled states are actually connected by some local unitary. So that means you actually start with one maximally entangled state, you can go to other maximally entangled states in that dimension with the help of the local unitary. And in fact, it is so special that local unitary is acting on only one part of the subsystem will do that. Although Ananda has written both UA and UB over here, but it can actually be done by local unitaries acting on one part of the subsystem.
I see. Okay.
Actually go to every other maximally entangled state by using just one local unitary over there on one particular subsystem. Number one. Second thing is that the Haar measure is important when we actually trying to integrate something. because over there what we have to do is that the integration has to be done with respect to some measure, and then those left covariant R measures are becoming important. So here in this particular case, what Ananda is trying to say basically that the fully entangled fraction is the overlap, or rather we should say the maximum overlap of rho with at least one of the maximally entangled states that we have over there. So what he will do, he is actually taking the overlap of rho with all the maximally entangled states possible in that dimension. Then he is choosing the highest one for that.
Yes, yes,
So on principle, actually we can calculate that. But if you come to the computational side of that, calculating exact fully entangled fraction for states is a very, very hard problem. For example, we can only do that for highly symmetric states like the Warner states, and also for the isotropic states, because Warner states and isotropic states have two very similar properties, that Warner states are like symmetric under the operation of tensor U star, and the isotropic states are symmetric under U tensor U. So over there, your Haar measures are important, because over there you see Horodoki's 1999 paper on this maximal singlet fraction, and also some other papers during that particular time. Then in those kind of cases, that when we integrate something like Haar measures are also important when we try to find out local hidden variable models. But as of now, in this particular case, Ananda is just trying to say that he is taking the overlap, the maximum overlap of the state rho with one maximally entangled state. So basically this fully entangled fraction measures the degree of proximity of a state with a maximally entangled state. If the degree of proximity is greater than some threshold, like for example in the 2-qubit case it is greater than half, then rho has to be entangled. Although in higher dimensions this is not true anymore. There may be some states whose fully entangled fraction is less than half, but less than 1/d, but still it is entangled. What we do in those kind of cases is we can use local filtering operations to increase the fully entangled fraction. So this is what he is trying to say, because he is trying to bring in this concept of fully entangled fraction to actually measure the proximity of his maximally entangled states.
Thank you for clarifying everything. Yes. Actually, that is as the name suggests, a fully entangled fraction is the overlap of the state rho with the one of the maximally entangled state. Yes, right. And if it is greater than half, it is entangled, and if it is less than half for all I, then it belongs to separable class. Yeah. Thank you. So may I proceed?
No, that is wrong. If it is less than half, it would be separable. That is wrong.
No, for all I.
No, even for all I.
Yes. Yeah.
That is what I said, that the converse of this statement is not true.
Right. Yeah. Sorry. Yeah, you're right. But it must hold for separable states. You cannot comment, but for this. But
yes.
Yeah.
For separable states, fully entangled fraction will be less than equal to 1/d, but the converse is not true.
Exactly. You cannot comment even if you get less than half, then you cannot comment. But yeah, for separable states, this condition must has to hold. Yeah, true. Yeah. Thanks. Thank you for clarifying everything. Yeah. So then again, there are some other basic things. So I need to define the entanglement measure, because that is what we are going to use just from the next slide onwards. So what is it? It is just a functional which should, if when you take this functional, let's say if the state is from the set of separable states, then this functional should give you the value 0. And if it is, it should not. If the map is LOCC, then this map acting on this state rho will, if it gives some another state sigma, then this functional E would always give the larger value for rho than this sigma. So that means what do I mean to say? That this measure or this functional should not increase the value of the entanglement if you are under some T operations. Here it's the LOCC. And there are some 3 types of entanglement measure that we are going to use here. One is the relative entropy of entanglement, and relative entropy, you all know that is just trace of rho log rho minus log sigma. And whenever I'm trying to talk about relative entropy of entanglement, you have to take the distance from the set of separable state sigma. Here I should denote by some different s, because yeah, maybe I can call relative entropy as d. And yeah, so this relative entropy and entanglement is the distance from the set of the state rho from the set of all separable state, and you have to take the minimum distance. And negativity, what is negativity? Which is another entanglement measure, and you just take the partial transport of the state, take the one norm, because when you take one norm, the value, since if a state is entangled, then the value of this one norm will be larger than 1, and you subtract 1 and then just divide by half. If it is a separable, then it will be 0, because the partial trace will not give you the negative value, and it will be again 1 of the one norm, and it will be 0. And what about entanglement of formation? This is another entanglement measure, which is defined as minimum over all possible, minimum over sum over pi sa psi I, where your I am talking about the entanglement of fraction of the state rho, where rho is, let's say you write down your rho in terms of just you rewrite in the form of pi psi I, where psi I are the pure states. Then your entanglement entropy is defined as you just take the partial trace of this state psi, and it's just trace of rho a log rho a, where rho a is the, you just taking the partial trace of this state psi. And in this way, the entanglement of formations are defined. So anyway, so these are some entanglement measures which we are going to use. That we are going to show that how these entanglement measures are used for the proof. So now, if I say again the state transformation rule for pure for 2-qubit pure state, the state transformation rules are given by the majorization criteria or the Nielsen criteria. Where let's say you have two states, psi and phi, where let's say you can also write the psi and phi in terms of the state vector. That means let's say xab and yab. So then you can go from xab to yab. When you can go from xab to yab, you have to first write this state in terms of Smith form. Let's say for the state xab, you write it in a Smith form, where this you collect the Smith coefficient xi, and you define a vector where you collect on not only collect the Smith coefficient, but you rewrite them in the non-increasing order, which is actually the n-dimensional probability distribution, because yeah, it's sum to 1, and you rewrite in the non-increasing order. So this is your x vector, and you also rewrite your y vector, which you collect your Smith coefficient from the state yab. And you will take this in the same way, like you collect the Smith coefficient and again write it in a non-increasing order, then you will get y. And if the Nielsen criteria says that for all such xy belongs to this Pn, which is the n-dimensional probability distribution, the transformation is possible if and only if for all I such kind of conditions hold. That means x1 is less than y1, less than equals to y1, x1 plus x2 will be less than equals to y1 plus y2 in this way. And you have to check for all such I or such j. So here we will say y majorizes x, or you can actually go from xab to yab if such conditions hold. So for example, let's consider this state. Let's say 1 by 2, 0, 0 plus 1, 1 plus 2, 2 plus 3, 3. And another state is just 0, 0. So you write its Smith coefficient, and you will see that it's 1 4 1 4 1 4 1 4. So it's already in the non-increasing form, and you write the Smith coefficient corresponding to 0 0, which will be 1 0 0 0. It's already, I wrote it in the non-increasing form. Then the majorization holds if such kind of relations holds, as I mentioned in the previous equation. So it's 1 4 less than 1, 1 4 plus 1 4 less than 1 plus 0. So it holds. So that then you can go from here to there, like that. So also another way to represent is the majorization curve or Lorentz curve. So you just let's say there are corresponding to your x and corresponding to your y, you can plot a curve Lx or Ly, which is nothing but a piecewise linear curve in R2, and that are defined by joining the points k, and k means let's say you are first taking this k is the 1 or 2 or 3. Let's say you have for this kind of states, the k will be 1 2 3 4. So here take the k, and sum over xi, which is again already written in the non-entangling form, sum over these things. So if you join this, if let's say you draw the line for Lx and you also draw the line for Ly, and if two curves touch each other, then you cannot go from one to another. So neither x may measure y nor y measures x. But my point is that for such kind of state transformation rules are only known for pure two-party system only. I mean, you cannot. There is no such concrete criteria for multipartite state transformation, as well as there is nothing for the mixed states. So only for two-party pure state you can have such kind of rule where it completely characterizes the state transformation laws. So for example, let's say this is a phi d plus, which is just, let's say 1 by root 3 0 plus 1 1 plus 2 2. So this we will call the maximally entangled state, because any states of let's say belong to that Hilbert space, the set of density matrix of that Hilbert space by LOCC. So that is why this is the maximally entangled state. So for example, the Bell state, you can go any state of two qubits, any two qubit state you can create from the Bell. You can go to any state from the maximally entangled two qubit state, which are the Bell state. So that's why we are calling it maximally entangled. And it actually it can be shown that all the entanglement monotones are actually maximizers for that particular state. So that's what we call maximally entangled state. But then the problem arises, can we define a notion of maximally entanglement in a given set? Like, let's say you have a set of states which does not contain that so-called maximally entangled state, which is the pure state. So let's say we have a set of mixed state. Then what is the maximally entangled state on that set of states? That is the question. Is there a notion of maximally entangled state on that particular set when actually, let's say if your set contains all the pure states, then definitely, let's say I am in the two qubit scenario, then definitely the Bell state is a maximally entangled state. So now I redefine my set where the two qubit Bell state is not there. So I have some finite set where there are some states, and those states does not contain that maximally entangled state, the pure state. Then among those states, can I define the notion of maximally entanglement? Like, what does it mean? Like, you can actually go to any other state of that set from that state. Then I will call it a maximally entangled state. Nonetheless, all the entanglement measure will also be maximized for that state. So can we define that notion of maximally entanglement in a given state? So here is a definition. Let's say given a set of states X, a state rho belongs to X, this set, we will call it maximally entangled if it holds that you can go from rho to sigma via LOCC for all sigma belong to this state X. So if it exists at all. So that is the question. Can we define that notion of maximally entangled for a given set? Okay. Yeah. Now, again, one can, the question may be a little bit less precise. Let's make the question more precise, because let's say now we fix the spectrum. Because if you fix the spectrum means, let's say you have a states which has, let's say your phi plus, phi minus, and psi minus, these four states. So they have eigenvalues only one, like 1 0 0 0. All the states are isospectral, means they have same purity. So now whenever we are trying to ask the same question, that maximally entangled state in a given set, we should also ask in same level of mixedness or same level of purity. So then if I fix the spectrum of the states, then the purity, the level of purity or level of mixedness is also fixed, right? Because you can go from one state to another by some unitary if I fix the spectrum, right? So then the question is, does there exist a maximally entangled state in this X, where I define this X here, such that, yeah, they all have the same eigenvalues. Let's say that we have a set of states which have the same eigenvalues. Then can we define the notion of maximally entanglement in that set of mixed states? Because I am not allowing any pure state there. So that is the question. And the author is going to answer it in the negative way. So is there any question so far? Hello, am I here?
Yes, you're audible. Yes.
Okay. Thank
You
you.
proceed.
Yeah. So then this was the result in 2001, where this versatility detail showed that, let's say you have a state with these eigenvalues lambda 1, lambda 2, lambda 3, lambda 4. So any spectrum distribution arranged in non-increasing order. Then they showed that a unique maximizer up to local unitary equivalent. Whenever I am saying about this, it's up to local unitary equivalent of the entanglement of formation, relative entropy of entanglement, and negativity among all 2-qubit states with the same spectrum. Such class of states is actually maximizing the all these three, at least these three this entanglement monotones or entanglement measure. This such class of states where this row lambda is lambda 1 phi 1, lambda 2 0 1 0 1, lambda 3 phi 2, and lambda 4 1 0 1 0, where phi 1 and phi 2 are defined earlier. Yeah.
Ananda, this is written in spectral decompositions, right?
Yes.
Is this things written in spectral? So that means this phi 1 and phi 2 are in the span of 0 0 and 1 1. Right?
Yes. Yeah. Here, sorry. Yeah. Just a minute. What happened?
Okay.
Yeah. Here I define the phi 1 and phi 0. Yeah, you can see here phi 1 and phi 1 and phi 2. Yeah. So
Okay. Thank you.
yeah. So such the class of states actually maximizes if you are in the isospectrum states, then such class of state will maximize these three entanglement monotones they showed. Then they ask the question, is it general for all entanglement monotones, or this is some special or some accident that okay, these three entanglement monotone is actually maximizing these things? Then they do some they ask the question whether this is some accidental or actually this is the particular states which is actually maximizing all these things. So then they keep it open whether this is actually maximally entangled or not, because see, all these entanglement monotones are maximized by these particular states. Then you can actually you can think of like, okay, I can go from all other states of that same spectrum from this state, right? Because it's a maximally entangled, because it's maximizing that three entanglement measures. So in some sense, intuitively, it can be that time people are thinking that, okay, this is the maximally entangled state of that. If I consider some particular state of spectrum, lambda 1, lambda 2, lambda 3, lambda 4. Okay, so for this work, let's consider the rank 2 instance of this paper, and we will consider just rho lambda is lambda phi 1 and 1 minus lambda 0 1 0 1. These two things, first two terms. And sigma lambda, which is just a mixture of these Bell diagonal states, but here only two Bell diagonal terms are there, phi 1 and phi 3, lambda phi 1 and 1 minus lambda phi 3, where lambda belongs to half and 1. So they are isospectral because you can also see that, yeah, this eigenvalue lambda 1 minus lambda, again, this is also lambda 1 minus lambda. So then they are showing first that there exists no map lambda, as we are now in the 2-qubit scenario, so from D2 to D2, such that lambda rho lambda equals to sigma lambda. Means you cannot go, there exists no non-entangling map. So I will now show that, or what they are showing is, if you consider the lambda as a non-entangling operation, then you cannot go from rho lambda to sigma lambda for such some parameter range of lambda. So what does it mean? So actually, but we showed earlier they showed that actually these three entanglement monotone or measure, like entanglement of formation, relative entropy, and entanglement and negativity, they are actually maximizing. So they are thinking that okay, rho lambda may be the maximally entangled state, but we will, so that even with the same spectrum, if you consider some different state sigma lambda, there exists no non-entangling operation. You can go from here to here for this lambda. So the proof is very simple. I can come. So yeah, depending on the time, but yeah. So once you show it for it holds for non-entangling operation, that means you cannot go from rho lambda to sigma lambda via non-entangling operation. It's also true that you cannot go by some lower class operation, which is LOCC. You cannot go from LOCC via LOCC from rho lambda to sigma lambda. So then we are done. So, but what they are showing is for non-entangling operation. Okay. So I can also prove the theorem. How much time I have, then I can decide whether I'll show the proof or not.
No, I think you can take little more time to just
Okay.
to discuss this because you have to finish by today. Okay.
Okay. Yeah.
But okay, you have let's say you have a
15 minutes.
15 minutes.
Okay.
15
Fine.
minutes,
Fine.
yes.
Fine. Okay. So then let's say okay. The proof is very simple. So let's say there exists some map lambda which can actually we can go from lambda rho lambda to sigma lambda. We assume it that there exists, and we will show some contradiction. Okay. So then what happens if you apply lambda on rho lambda? You will get lambda. What was my rho lambda? Let's define it. Rho lambda was lambda phi 1 plus 1 minus lambda 0 1 0 1, and my sigma lambda was lambda phi 1 plus 1 minus lambda phi 3. Okay. So then what happened? So if you apply lambda on this rho lambda, you will get lambda phi 1 plus 1 minus lambda 0 1 0 1, right, equals to sigma lambda, which is lambda phi 1 plus 1 minus lambda phi 3. So by the way, what do I mean by phi 1 and phi 3? Phi 1 is actually I am saying phi 1 phi 1. So that density matrix. So that I am just taking. I forgot to say. Yeah. So let's say this kind of operation holds. So then let's take the trace of phi 1 and sigma lambda. So then what we will get from this direction? What we will get? It will be just lambda, because this is orthogonal. Phi 3 is orthogonal. So we will take only lambda from this part. Let's take trace of phi 1 sigma lambda phi 1. Take trace of phi 1 on the both side. Then we will get lambda from this side. Will be lambda phi 1 trace plus 1 minus lambda trace of phi 1 lambda 0 1 0 1, right? Yeah. So again, this will be less than lambda trace of phi 1 lambda phi 1 plus 1 minus lambda by 2. Because why? Because we know that this is separable state 0 1 0 1. So as I saw earlier that the trace of phi 1 lambda 0 1 will be less than half, right? Because from the properties of the since lambda is non-entangling, so lambda 0 1 0 1 will belongs to the separable, will belong to set of separable states. So then if it is a separable, then it will be less than half. So it's 1 minus lambda by 2. So then you will get this. And if you just simplify, you will get trace of phi 1 lambda phi 1 is actually greater than 3 lambda minus 1 by 2 lambda. Just simple calculation you will get. Now, analogously for this, you can also consider, let's take trace with phi 3. Let's just consider sigma lambda. Once I am taking the same this state. Yeah, sorry. Here, this is the state, and let's take trace with multiplying phi 3. Then what we will get? We will again get from this part. It will be 1 minus lambda from this part, and this 1 minus lambda will be equals to lambda from here. It will be trace of phi 3 lambda phi 1 from this equation 1. You can think of lambda phi 1 plus 1 minus lambda trace of lambda phi 3 lambda 1 0 1 0 1, right? So then again you can show that it's actually less than from the same analogy, because since this is 0 1 0 1 and this lambda is a non-entangling operation, so this term will be less than if you take the trace of phi 3, this will be less than half, as I showed earlier, the fully entangled fraction. So it's lambda trace of phi 3 lambda phi 1 plus 1 minus lambda by 2. So same thing. And this implies again trace of phi 1 phi 3 lambda phi 1 is actually greater than equals to 1 minus lambda by 2 lambda. So let's say I call this as equation say 2, and I call this as equation 3, and I call it equation 4, and I call it equation 5. Okay. So then, so if we consider now both together, so what will happen? So let's say we have the expression trace of phi 3 lambda phi 1 and trace of phi 1 lambda phi 1. So let's consider that both things together. So trace of phi 3 plus phi 1 lambda phi 1, because here is lambda phi 1, here is lambda phi 1, and here phi 3 and phi 1. So let's just consider both things together. And then this is greater than 3 lambda minus 1 by 2 lambda plus 1 minus lambda by 2 lambda. I am just adding the two things, and you can see this is a 1. Nonetheless, you can also see, sorry, what happened? Oh. Yeah. So nonetheless, yeah, you can also you can also show that this is also less than 1. Why? Because again, you can see that lambda is non-entangling, right? So then lambda phi 1, so if lambda is non-entangling, then lambda phi 1 yeah, so then if lambda is non-entangling, then what happened? Yeah, so if lambda is non-entangling, then this term will give me yeah, so this phi 3 and phi 1, how?
Ananda, I think you can take the dual of this lambda over phi 3 plus phi 1, and phi 3 plus phi 1 is a separable.
Oh yes.
I think you can take the dual of this lambda over phi 3 plus phi 1 together, and phi 3 plus phi 1 is a separable, so that can take maximum 1 value, because individual for half. Because I think dual of the non-entangling would be non-entangling, something that kind of argument. I don't know.
Yes, I think why this should hold. If you take the dual, then lambda phi 3 plus phi 1, that is you are saying, yeah, that is separable.
Phi 3 plus phi 1 is a separable. Yes.
Yeah. So yeah. So again, that can be maximum. Yeah. So it will be maximum 1.
Maximum 1. Yes.
Yeah.
It will be always less than equal to 1.
Yeah. So then, since this is less than equals to 1 and also greater than equals to 1, so that means actually the equality hold. So that means actually trace of phi 3 plus phi 1 and lambda phi 1 is actually 1, right? Because the equality must has to hold. So then if this holds equality, then you can see that here this equality also has to hold, like here this one and this one. Because we are actually taking, see, this less than this and this less than this, like and we are summing it, these two things. So then actually this equals to this and this equals to this corresponding to this. So that equality also has to hold. And then
yes.
Yeah. So and then if you see, so let's say if I consider the second term, which is this trace of phi 1 lambda 0101, and this trace of phi 1, this term, see, this trace of lambda trace of phi 1 lambda 0101, and similarly if you take this 1010, so we will see that the trace of phi 1 lambda 0101 and equals to trace of phi 3 lambda 1 0 1 0, and that will has to be 1 half. And then what they consider, I mean, I'm just giving the hints of the proof, which is very simple, because let's just I mean, maybe there are some I'm not giving the proof in very concrete form, but I'm just, let's give the hints how the proof is done. So then we need to the equality must has to hold, and then you consider some another state tau, which is just a mixture of you to take the state such that it's the coefficients are not greater than half, so that it's a separable state. Say, let's say 1 4 1 4 phi 1 plus phi 4. So if you write the phi 3 plus phi 4, again that will be half phi 1 plus 1/4 0 1 0 1 plus 1/4 1 0 1 0, right? Because that is the phi 3 and phi 4. If you sum it, you will get 0 1 0 1 plus 1 0 1 0. But this state is a separable state, because none of the coefficient is greater than half. It's maximum half. So this is a separable state, right? But if you calculate from the earlier things, like if you calculate the trace of phi 1 lambda tau, where I am actually, let's say, apply lambda on this state. If you apply lambda, apply this non-entangling operation on this state tau, and you take the product with phi 1 and then take the trace, then you will see that actually it will be greater than 3 lambda minus 1 by 4 lambda plus 1 by 8. And if you take lambda greater than 2/3, then this implies that this is greater than half. This is greater equals to half. If you take lambda strictly greater than 2/3, if lambda is this. But since this state is a separable state, and you apply non-entangling operation, and you know that this state should not be entangled, but you are coming to some contradiction that actually, if you take the trace of phi 1 and lambda tau, since phi 1 is maximally entangled and you are taking, then it is giving me greater than half, which is entangled. So there is some contradiction, and so what do we conclude? We conclude that if lambda greater than 2/3, lambda tau is entangled, and since we choose tau as separable state, we have to conclude that lambda is non-entangling operation is not true. So what we choose earlier. So then you cannot go from rho lambda to sigma lambda via some non-entangling operation. There exists no such lambda for at least for this range, 2/3 to 1. So in this range, you cannot, I mean, at least for that range, we are showing that you cannot go from rho lambda to sigma lambda. That is the conclusion. Okay. So the proof, you can see the proof in details, which is very easy. I mean, I just give the brief outline, but this is the conclusion. So then the corollary is that there is no maximally entangled mixed state for a fixed spectrum in general. Because why? So by theorem 1, we are showing that you cannot go from rho lambda to rho if rho belongs to the set of states which have same spectrum, lambda 1 minus lambda. You cannot go from rho lambda to rho via LOCC, because we saw it for non-entangling operation, and then it is also true for LOCC. So we cannot go from rho lambda to lambda. But the previous paper in 2001, this versatility detail, they showed that there exists an entanglement measure such that your all entanglement measures, like not all, the entanglement of formation, relative entry of entanglement, and negativity, they actually give the measure higher measure than this E rho. Means E for rho lambda greater or equals to E rho for any rho belongs to D with the spectrum lambda 1 minus lambda. So then you cannot, if this some entanglement measure gives the higher value for rho lambda than rho, then you cannot go from rho to rho lambda via LOCC. So then, yeah, you cannot neither go from rho lambda to rho, as it has been proven in theorem 1 via LOCC, although it has been shown for a non-entangling operation. And the previous result suggests that you cannot go from rho to rho lambda because there exists some entanglement monotone which you cannot go from rho lambda to from rho to rho lambda. So then there exists. So if as I defined earlier, what is the notion of maximally entangled? You cannot go from if it is a maximally entangled state in that particular set of states, then you should go to any states of that set from that particular state, right? But here you see you cannot, although if you define some notion of maximally entangled for the rho lambda, you cannot go to rho even with the set of all the isospectral states. So then is it
Ananda, you have 2 or 3 minutes more. Okay?
Yeah, this is my last slide. So then there is a another corollary, that is it the then as you so as we saw that in the theorem 1, the rho lambda is actually you cannot go from rho lambda to rho or the sigma here. And we already saw earlier that it was shown earlier that the some of the entanglement measure are giving higher value for rho lambda than rho. Then we should have also some entanglement measure here, E of rho lambda, we should also give greater than E of rho, right? And that is also you can actually find how. So the corollary 2 says there exists choice of lambda for which the states rho lambda do not maximize all entanglement monotone among all states with the same spectrum. How? So let you define PLOCC, probability of PLOCC from rho to sigma, and P any rho to sigma, which denote the optimal probability of converting rho to sigma here respectively by the free operation LOCC and the non-entangling operation. And then the paper by Gupta Vidal, he showed that for any given state rho, let's say you fixed your state rho, then the PLOCC, that is the optimal probability of converting rho to sigma via LOCC, is an entanglement monotone as a function of rho. Okay, now what I mean to say, like let's say you consider a state rho. So yeah, so here let's say you want to have some E lambda, which is another entanglement measure for some state rho. Then you consider the PLOCC, the optimal probability of converting rho to sigma. Let's say we define the PLOCC as, now here you have to fix the sigma. Let's say we fix the rho to here the sigma lambda, or
but
itself.
The sigma has to be entangled, right? Sigma
Sorry?
has to be entangled. Sigma has to be entangled.
Yeah, sigma has to be entangled. That's true. Yeah. So then, if you consider this, then the PLOCC is I fix the sigma or the state where we want to go itself as sigma lambda. Okay, the sigma lambda. This is now my new entanglement monotone. And then E lambda, sigma lambda, what is the probability of optimal probability of converting sigma lambda to sigma lambda? It will give 1. So then E lambda, sigma lambda is 1 for some particular lambda range. But by theorem 1, we saw that actually you cannot go from rho lambda to sigma lambda by the non-entangling operation. And since then by PLOCC rho lambda to sigma lambda, it's a strict, it's either less than equals to P any rho lambda sigma lambda, which is equals to E lambda sigma lambda. Then this is less than equals to P any rho lambda to sigma lambda. And since you cannot convert from rho lambda to sigma lambda concretely, this should be less than 1. So then there exists, this is the entanglement monotone for which the sigma lambda is giving maximum value, but rho lambda is giving less value. Yeah, it's higher than this. E lambda sigma lambda is higher than E lambda rho lambda. So that is also the entanglement monotone corresponding to that. So that is the conclusion. So then what is the conclusion? The conclusion is that for such set of states, let's say you fix the spectrum of the set. Let's say you have a set of states which has fixed spectrum, then you cannot define the notion of maximally entangled on that particular set of states. Like you can go from one to another and another to another. So there is some contradiction. So that was the main theme of the work. So yeah, thank you.
Okay, now we can take some questions.
Yes, sure.
1 or 2 questions we will take.
I'm sorry.
So if anyone has any query or any questions, please come forward. If I think no one has any questions, you have mentioned it clearly. I think it is already quite late, so
Yeah,
we
yeah.
can end the meeting right now.
Yes,
But okay,
sorry.
thanks for the thanks. We can
Yeah.
thank Ananda for his nice
Yes.
talk and
Thank you for being there. Yeah.
okay.
Thank you, Anand. Thank you.
Thank you for being here.